Today, we're going to do more practice with statically indeterminate axially loaded members. These problems can be kind of tricky. The process is going to be the same every time. We're going to have a free body diagram. We will use equilibrium equations to solve for as much as we can, and then we will need a compatibility condition to put it all together. I picked a couple of trickier problems where we have to do a little more work on the compatibility to do today. This first one is a bar, and it says it is pinned at A and supported by two aluminum rods. So that would be CD and EF that are my aluminum rods. Gives us their diameter of 1 inch, and they both have a modulus of elasticity of 10 times 10 to the third KSI. Supposed to assume this bar is a whole lot more rigid and stiff compared to these thin rods. And we assume that it starts out horizontal before we apply any forces. And then what we're going to do is apply a 5 kip force to the end. And the problem is us to find the force in each rod once we apply that 5 kip load. So hopefully you can see that what will happen is when you apply this load, it's going to rotate to a new position, and these two bars are going to stretch out by different amounts, and so they're going to have different amounts of force in them. And when we draw the free body diagram in just a second, you'll see that we can't solve for the forces in these bars using statics alone. That's what makes it statically indeterminate. For our first step, I want to just draw my whole free body diagram. So what I'm drawing it of is this bar, because these two rods are attached to that bar. They're going to be pulling up on that bar. That's where my load is being applied, and it's pinned at A. So I should be able to get a nice free body diagram of the bar. Doing that, I got my applied 5 kip force at the end. I've got my unknown AX and AY at the pin. And in member CD, if we assume it's in tension, it's going to be pulling up. And EF will also assume tension and pulling up. So we have a free body diagram. Next step after that is always to write equilibrium equations. If we sum forces in the x direction, we get the very useful information that AX is equal to 0. If we sum forces in the y direction, we get AY plus FCD plus FEF minus 5 kips equals 0. We can sum moments too. So let's sum moments about a point. How about point A? And if I sum moments about point A, it has to be 0. I have FCD will cause a counterclockwise moment, and its distance away is 3 feet. FEF will also cause a counterclockwise moment. Its distance away will be 3 feet plus 6 feet, 9 feet. And then clockwise, I'll have my 5 kips. And that distance away is 3 feet plus 6 feet plus 3 feet. So 12 feet. And that all has to equal 0. So that's another equation that might be useful later on. Those are two equations that have together 3 unknowns. I've got CD, EF, and AY. So 3 unknowns in those two equations. I can't solve for 3 unknowns with 2 equations. That's what makes it statically indeterminate. So my next step is I need a compatibility equation. Step 3 is to get a compatibility equation. All right, what I know about this is that point A is not going to move, but it can rotate, so I think the new shape is going to be down here. So this is a case where I'm going to actually draw a triangle and see if I can figure this out. So A is right here. Then we come over 3 feet and we get to point C. 6 more feet, we get to point E. And 3 more feet, we get to point B. Then we're going to rotate to some new position. If we assume that this bar is completely rigid, then because of that rotation, these points aren't going to go straight down. They're going to move both down and back a little bit. So we typically use small angles here and approximate things. So we're going to say that right there is my length change of member CD. Right there is my length change of member EF. And right there is going to be how far point B moves. And I know these lengths, right? The whole bar rotated. So we're going to say that this is 3 feet, this is 6 feet, and this is 3 more feet. We're calling that the length change of CD, calling that side the length change of EF. This triangle and this other triangle are similar triangles. So that's our next step to get our compatibility equation is we're going to use similar triangles. With the one triangle, we're just going to do the side opposite this angle over that one has got to be exactly matched by that side over that one. So we end up with The deflection of CD relative to the 3-foot side has got to equal the deflection of EF relative to the 9-foot side. I bring the 9 feet to the other side. If you do that, you get 3 times delta CD is equal to delta EF. That is the compatibility condition for this problem. It's a relationship that we get from similar triangles, that when this bar rotates down because EF is 3 times as far as CD, EF has got to stretch out 3 times as much as CD. Hopefully that's fairly intuitive. Our next step, once we have that compatibility condition, is we have equations up here that have forces. This equation has a deflection. We need to relate the deflections to the forces. We do that using our axial deflection equation. Delta is equal to force times length over A times E. So let's plug that in right here in place of our 2 deflections and write our compatibility condition with forces in it. We're going to get 3 times the force in CD, the length of CD over the area of CD, modulus of CD, is equal to the force in EF, the length of EF over the area of EF, times the modulus of EF. We need to go look at what those lengths are, those areas, and those Young's modulus values. They both have the same length, it is 4 feet. They both have the same diameter, it is 1 inch, and they both have the same modulus of elasticity. So as far as this equation is concerned, we can simply cancel out the lengths, because they're both 4 feet, the areas, because they both have the same diameter, and the Young's modulus values, because they all have the same material. So simplifying, this becomes 3 times the force in CD is equal to the force in EF. The math is super easy because those lengths, areas, and modulus values were all the same. If they were different, you'd need to plug in those different numbers into all of these spots and then simplify. So now let's plug that in with this equation. Only has CD and EF in it. So then if I combine it with this equation, I can solve. There's my equilibrium equation that I'm going to use with this compatibility equation. Let's combine them. We get 0 equals FCD times 3 feet plus FEF, which is 3 FCD times 9 feet minus 5 kips times 12 feet. Solving, we get that FCD comes out to be 2 kips and FEF then comes out to be 6 kips. And hopefully that makes sense. Does it make sense that we get numbers on the order of 2 kips and 6 kips? Well, considering that the applied load was 5 kips, I think it makes sense. We wouldn't expect 5,000 kips or 0.002 kips. That's all the problem asked for. The logical next question might be, what is the stress in CD and EF? So if I want to find the stress in CD, well, that's going to be the force in CD divided by the area in CD, right? This is just normal stress. You take the force over the area. So let's put in the 2 kips. If you would like, you can write that as 2,000 pounds. And we divide it by the area, pi times the radius squared. Do you remember how big the diameter was? The diameter was 1 inch. So the radius would be a 1/2 inch. We square that. The number comes out to be 2,546. We'll round that to 50. And the units would be pounds per square inch, so PSI. That's what I get for the stress in CD. Let's find the stress in EF. That's the force in EF divided by the area of EF, which is exactly the same. So I should end up with 6,000 pounds divided by that same area, pi times 0.5 inches squared. Comes out to be 7,640 PSI, because it should be 3 times bigger since the force is 3 times bigger and the area is the same. The other question that we could ask here would be, how big are those deflections? So what is the deflection of CD, the deflection of EF, and the deflection of point E at the end? Deflection of CD, let's do that one first. Delta CD is FCD LCD over area of CD modulus of CD. So the force is again 2,000 pounds. The length, do you remember how long it was? It was 4 feet long. So we put in 4 feet. The area we just found, pi times 0.5 inches squared. And the Young's modulus These were made of aluminum, so the Young's modulus was 10 times 10 to the third KSI. I'm not going to write KSI. I want to write that as kips per square inch. And in fact, this is a little easier if instead of 2,000 pounds, we write this as 2 kips, because then the kips will just cancel. So let's double check that our units are going to work out okay. The kips will cancel, and the square inches will cancel, and our answer would be left in feet. However, we're expecting a really small deflection, so we probably want our answer in inches. So why don't we convert that? Let's do a conversion factor. It'll take 12 inches to go 1 foot, and now our feet will cancel, and we'll end up with our answer in inches. So running that through my calculator, I get 1.22 times 10 to the minus 2 inches for delta CD. Small number, that's good, because all of our assumptions assume we have small deflections. Let's do EF. Actually, we can save ourselves some time with EF. Delta EF is just 3 times delta CD. So that will be 3.67 times 10 to the minus 2 inches. And finally, how do we get delta B? I guess I should have done another similar triangle up here. If we want to find delta B, I need to use the same similar triangle, delta CD over 3 feet. That was using the little triangle. Then I can use delta B over the entire 12 feet. I had delta CD was to 3 feet as delta B was to 12 feet. So that means delta B is 4 times delta CD, gives me 4.89 times 10 to the minus second inches. We solved the problem plus did a couple of extensions, and I really wanted to do these extensions because these units tend to cause students a lot of problems. Let's do a second example. Different kind of a problem, but also a more difficult compatibility condition. So what do we have going on here? We have 3 posts, A, B, and C, and it says that that center post B has an original length of 124.7 millimeters. The other 2 are a full 125 millimeters. So before this gets loaded at all, there's a little gap right here. Then it gets loaded with these 800 kilonewton per meter distributed loads. We're assuming that these caps do not bend or deform at all compared to the posts. And then the question is actually to find the average normal stress in each post. The posts are all made of aluminum and they all have the same cross-sectional area. Just like the last problem, we are going to start with a free body diagram and equilibrium equations. Then we're going to write compatibility conditions. And finally, we're going to solve everything simultaneously. First up, a free body diagram. And I am going to assume that the loading is big enough that it's actually going to close the gap. So we're going to compress down to some distance farther than the gap. If it turns out you don't actually close that gap, you would need to resolve this, assuming you don't close the gap. And in that case, it's really easy to solve for the stress and the force in these two because it's no longer statically indeterminate. So we're assuming that it closes. I'm going to draw a free body diagram of one of these caps. Either the one on the top or the bottom will work. I'll do the one on the top. So what is acting on that top cap? Acting on top of it is a distributed load. I just like to immediately replace those with what they're equal to. So it's going to be a downward force acting at the middle of that rectangle, the centroid of the rectangle. Its magnitude will be 800 kilonewtons per meter times the distance it acts over. What we're really doing is finding the area under this rectangle. So the magnitude of this way is 800 kilonewtons per meter. And how wide is that? Well, in the picture, I've got 100 millimeters and another 100 millimeters. So it'd be 200 millimeters, but in meters, that's 0.2 meters. Multiplying that out, I get 160 kilonewtons. So that's the downward load applied to that top cap. Pushing back up on it is going to be the force in member A, the force in member B, and the force in member C. I'm just going to draw them the direction I know they're going to act. The columns will actually all be in compression. Okay, there's my free body diagram. Next step would be equilibrium. There are no forces in the x direction, so let's sum force in the y direction. And we get the force in A plus the force in B plus the force in C minus 160 kilonewtons equals 0. We will probably use that at some point. And then we need to sum moments about a location. I think I want to sum moments about this point right here. Should we call it point B? And summing moments about B is 0. The reason I like that location is that knocks out both a force and the distributed load. Neither of those will cause a moment about point B. So summing moments about point B equals 0, we would have the force at C times 0.1 meters causing a counterclockwise moment, and the force at A times 0.1 meters causing a clockwise moment equals 0. We can actually solve and determine that FA is equal to FC. So that's helpful. We've got 2 equations, but 3 unknowns. So we can't solve it yet. So we're going to need to do our next step, which is compatibility. And since this is completely symmetric, there's no reason that this cap would tilt. I think it's just going to move straight down. So the new deformed shape would be right here. So however far A and C deflect downward, B is going to compress a little bit less because of the gap. So the way we write that is to say that the deflection at A, which is the same as the deflection of C, is equal to deflection at B plus a little bit. How much is that little bit? Well, it's going to be the difference between the 124.7 and the 125. So just this little tiny gap, we're going to find out how big of a difference it makes in the force in these pillars. So it's 0.3 millimeters. We can't leave it like that. Our next step is going to be to use our delta equals FL over AE equation in here. So my compatibility equation then is going to become force in A times the length of A over the area of A times the modulus of A has got to equal the force at B, length of B over area at B, modulus of B, plus 0.3 millimeters. In our last example, we were able to cancel out a bunch of areas because they were the same and a bunch of modulus values because they were the same. In this problem, did you notice the areas are the same and the moduli are the same for all of the different pillars? The problem is we can't cancel them out because there's this other term. So we are going to have to plug in all the numbers and actually simplify. So let's plug them in. This becomes FA, the length of A, how long was it? 125 millimeters was the original length. So we'll plug in for now 125 millimeters. The area was 400 square millimeters, and the Young's modulus was 70 gigapascals. On the other side, that's going to equal FB. The length of B was 124.7 millimeters. Remember, it was just a little bit shorter, but the area is still 400 millimeters squared, and 70 gigapascals is the modulus, plus 0.3 millimeters. I see a whole lot of students who from here can't get the units to work out. So I want to go through the units really slowly because this and this are probably not the most consistent units to work with. Let me do this on aside for a little bit. So 70 gigapascals. What does that equal to? Well, that's 70 times 10 to the 9th newtons per square meter. You don't have to do it this way. You could convert everything to newtons and meters and solve. But there is a little bit of a shortcut here that I want to show you. There's 1,000 newtons in 1 kilonewton. There's also 1,000 millimeters in 1 meter, and it goes that way because the meters on the bottom needs to cancel with the meter on the top. Then I need another 1 meter over 1,000 millimeters. So look at what would happen if I did this conversion. The meter squared cancel the meters. The newton cancels the newtons. And now look, I've got 10 to the 9th. And on the bottom of the fraction, I've just created 10 to the 3rd, 6, 10 to the 9th on the bottom. The 10 to the 9ths actually cancel. So what you get is 70 kilonewtons per square millimeter. A gigapascal is equal to a kilonewton per square millimeter. It's a really helpful thing to memorize because you're often given area in square millimeters. So if I can just replace that gigapascal with kilonewtons per square millimeters, those square millimeters will cancel out. I'm going to rewrite this equation. I've got FA times 125 millimeters over 400 millimeters squared times 70 kilonewtons per square millimeter. That's what a gigapascal is. That equals FB times 124.7 millimeters divided by 400 millimeters squared times 70 kilonewtons per square millimeter. And then don't forget, we've also got the plus 0.3 millimeters. Now, the millimeters squared cancel. Let's get those out of there. And so when we multiply these two things on the bottom, we're going to get a number that has units of kilonewtons. And let's just multiply the whole equation through by that. So what we end up with when we do that is on the left, we have FA times 125 millimeters equals FB times 124.7 millimeters plus 400 times 70 is 28,000. You multiply it then by the 0.3 and you get 8,400, and the units will be kilonewtons times millimeter. Let's just divide the whole thing through by millimeters. Then the millimeters all cancel out, and we just have an equation that says FA times 125 equals FB times 124.7 plus 8,400 kilonewtons. There's our simplified compatibility equation. Now, what do we need to solve it simultaneously with? Probably this equation with this plugged in. So it's FA plus FB plus FC, which is also FA. So we got two FAs plus FB equals 160 kilonewtons. Let me write that down. Our other equation ended up being 2 times FA plus FB equals 160 kilonewtons. So two equations to solve simultaneously. So let's just go through the steps. When I have equations like this, I like to try to get the same factor in front of two of them. So for example, if I could have 125 in front of FA in this equation and have a minus 125 in front of FA in that equation, then I can add the two equations. Let me write them down one more time. So I got 125 FA minus 124.7 FB equals 8,400 kilonewtons. That's what my first equation ends up looking like. Second equation, I want to multiply the whole thing by whatever half of 125 is. 62.5. Multiply the whole equation by 62.5 minus. I'll end up with minus 125 FA minus 62.5 FB equals minus 10,000 kilonewtons. Then we just sum these two equations. We add them up. The 125 FA minus 125 FA becomes 0. The next term becomes minus 187.2 FB equals minus 1,600 kilonewtons. So solving FB comes out to be 8.547 kilonewtons. And now we can substitute that back into either that equation or that equation to solve for FA. Doing that, we get FA is 75.726 kilonewtons. Keeping extra decimals right now because I next need to convert these into stresses because that's what the problem was asking. These are both in compression. I drew them in compression. They came out positive, which means I was correct. Next step is to find stress. So the stress in post A and the stress in post C, they're going to be the force in A divided by the area. So 75.726 kilonewtons, the area was 400 millimeters squared, comes out to be 0.189 on my calculator, and the units are kilonewtons per square millimeter. Do you guys remember what a kilonewton per square millimeter is? We just did it. It's a gigapascal. So this is 0.189 gigapascals, or you could call that, multiplied by 1,000, 189 megapascals. Either one, I'm totally fine with either answer. Both correct. Also in compression. What about the other one? Stress in B, it's the force in B divided by the area. So that's 8.547 kilonewtons. And that's area is also 400 millimeters squared. This one comes out to be 0.0214 kilonewtons per millimeter squared, which is 0.0214 GPa or 21.4 megapascals, also in compression. So the thing you might find surprising is that with only a small 0.3 millimeter gap, we end up with member B has almost 1/10 the force of members A and C. So a small gap, small mismatches like that can make a really big difference in how much stress a different member sees. This one only sees 21 megapascals. The other one sees almost 200 megapascals. So 0.3 millimeters might not seem like a lot, but it does in terms of the forces and the stresses. Hopefully those two problems, they had much more complicated compatibility conditions. This one I think is really good practice for units as well, because it's so easy to make a mistake once you're adding on this 0.3. Some students would prefer to convert all of these to meters and convert these to meters squared and convert those to newtons per square meter. That's totally fine too, as long as you're careful and methodical. I usually actually leave most things in the units that they're provided and only convert if I find out later on I have to, because it turns out I didn't ever need to convert this 400 into meters squared because I could just cancel the millimeters squared on the bottom. And I didn't need to convert all of these to meters. As long as you have millimeters in every term, it's still consistent. All right, that's it for statically indeterminate extra practice problems for today.